In the mathematical field of category theory, the category of sets, denoted as set, is the category whose objects are sets. The arrows or morphisms between sets A and B are all triples where f is a function from A to B. Many other categories add structure to the objects of the category of sets or restrict the arrows to functions of a particular kind. Properties of the category of sets. The epimorphisms in set are the surjective maps, the monomorphisms or the injective maps, and the isomorphisms are the bijective maps. The empty set serves as the initial object in set, with empty functions as morphisms. Every singleton is a terminal object, with the functions mapping all elements of the source sets to the single target element as morphisms. There are thus no zero objects in set. The category set is complete and co-complete. The product in this category is given by the Cartesian product of sets. The coproduct is given by the disjoint union. Given sets I where I ranges over some indexed set I, we construct the coproduct as the union of I times I. Set is the prototype of a concrete category. Other categories are concrete if they resemble set in some well-defined way. Every two-element set serves as a sub-object classifier in set. The power object of a set A is given by its power set, and the exponential object of the sets A and B is given by the set of all functions from A to B. Set is thus a topos. Set is not abelian, additive or pre-additive. Its right zero morphisms or the empty functions x. Every object in set which is not initial is injective and also projective. Foundations for the category of sets. In Zermelo-Fraenkel set theory, the collection of all sets is not a set. This follows from the axiom of foundation. One refers to collections that are not sets as proper classes. One can't handle proper classes as one handles sets. In particular, one can't write that those proper classes belong to a collection. This is a problem. It means that the category of sets cannot be formalized straightforwardly in this setting. One way to resolve the problem is to work in a system that gives formal status to proper classes, such as NBG set theory. In this setting, categories formed from sets are said to be small and those that are formed from proper classes are said to be large. Another solution is to assume the existence of Grothendieck universes. Roughly speaking, a Grothendieck universe is a set which is itself a model of ZF. The existence of Grothendieck universes is not implied by the usual ZF axioms. It is an additional, independent axiom, roughly equivalent to the existence of strongly inaccessible cardinals. Assuming this extra axiom, one can limit the objects of set to the elements of a particular universe. In one variation of this scheme, the class of sets is the union of the entire tower of Grothendieck universes. However, one does not work directly with the category of all sets. Instead, theorems are expressed in terms of the category set whose objects are the elements of a sufficiently large Grothendieck universe U, and are then shown not to depend on the particular choice of U, as a foundation for category theory. This approach is well matched to a system like Grothendieck set theory in which one cannot reason directly about proper classes. Its principal disadvantage is that a theorem can be true of all set U but not of set. Various other solutions, and variations on the above, have been proposed. The same issues arise with other concrete categories, such as the category of groups or the category of topological spaces.